Hello, welcome back, ladies and gents. Back to further maths today, surfaces of revolution. I did look today actually in which particular module with Pearson Edexcel this particular topic is, and I think they call the topic Further Pure 2. I don't know what that actually means. My understanding is of the fourth pure module in the order you meant to have them. Okay, we're going to have it in parametric, so we're having parametric equation, cycloid of some sort. X is equal to theta minus sine theta, and y is 1 minus cos theta, and the curve is defined between 0 and 2 pi, so probably just one cycle of the cycloid, and we're going to do the surface of revolution about the x-axis and get the answer in exact form. Okay, is this difficult? I don't know. It's in one of my papers, and therefore I didn't really look at the solution, and sometimes I need to look at the solution to see how long it is, what kind of stuff it involves. I didn't look at it, I'm afraid. I just picked up the question. So we're going to find out how tough this is. Okay, here it goes. Standard result, surface of revolution is 2 pi y, and if we are in parametric, we're gonna be integrating from theta 1 to theta 2, y of theta, or you can just write y, it doesn't really matter. And then we're having the length of the curve, d little s, and the d little s in parametric is going to be dx by d theta all squared plus dy by d theta all squared, close your square root, and of course the integration is with respect to theta. We are in parametric, so it's some kind of integral. We'll see in a second how tough. Probably not tough at all. We'll see what we're getting for something like this. It's definitely going to be trigonometric. Okay, so let's start putting our bits in. 2 pi. Then we have the limits. The limits are, of course, because the whole curve, and we're going to you can see the entire curve is above the y-axis, so we don't have to worry about things, because if you look at the y is the theta runs between 0 and 2 pi is 1, and then of course this particular quantity will be subtracting when it goes under, so it runs between 0 and 2, so it's entirely positive. So it's going to be from 0 to 2 pi. Y as a function of theta is of course 1 minus cos theta in a bracket, and then we got the square root. So this is now normally this type of integrals where the action is, and how difficult will it be, we'll see in a second. So we need dx by d theta. Differentiating, that's no problem. Dx by d theta is going to be 1 minus the cos of theta, okay, all squared. So that's my dx by d theta, and my dy by d theta is going to be a sine of theta all squared plus the sine of theta all squared. I'll write it like this, of course, and then it's my d theta. And now I need to simplify this integral. Okay, that's not a problem. So that is equal to 2 pi limits as before. Let's tidy up the radical. So 1 minus cos theta. If we expand this, we're going to get a 1 minus 2 cos theta plus a cos squared theta. That's this bit here, plus a sine squared theta. And of course, these two quantities will condense into a 1. And therefore, this is going to be the square root, okay, of 2, that's the 1 plus the 1, 2, minus 2 cos of theta, d theta. So we managed to simplify that to something a little bit more reasonable. Now is what needs doing next. Well, that's exactly the same as that, isn't it? If we factorize a 2 out of the square root. So I'm going to do that. And I think that's quite straightforward, isn't it? Let's put I'm going to factorize a 2 out of those two terms, pull it outside the square root, and then move it outside the integral, so it's not in my feet. So it's going to be 2 pi square root of 2, 0 to 2 pi. And I'm going to have the 1. Hope we can see the board where I am. Sorry, I might be in the way. I'll move out of the way if I'm blocking your view. 1 minus cos theta, and the square root I'm going to write to the power of a half is going to be 1 minus the cos of theta to the half d theta. And on the next line, this is going to be 2 pi root 2, 0 to 2 pi, 1 minus cos theta to the power of 3 over 2. And that is now not so nice. So I need a bit of thinking time myself, because I haven't done surface of revolution. Surface of revolution, sometimes they produce certain type of integrals, and you need to have done quite a few of them recently to just come across a few of these techniques. So this is not the kind of integral you're likely to see in any in other parts of mathematics. It's typical for this kind of work. So let's think how we're going to do that. Okay, I know how to do this. It just came to me. I'm going to write some workings up here so we can actually see the manipulations. We need a little bit of trig. So let's wipe off all of this. In fact, I don't need that, so I'm going to go S and start writing on this line when I'm ready. I'm just going to leave the very last line so you can actually see what kind of manipulation. I think this particular manipulation comes a lot in this type of work. I did say actually before that you need to, there's certain things that they're kind of repetitive, and if you're doing loads of this, they come up a lot of the time. You're going to need to look at your double angle for cos, okay? The cos of 2 theta is, of course, I'm going to write it as, which way do I want it in there? Try to picture which version I need to show you in there. It's the sine one. 1 minus 2 sine squared theta. Okay? Is this a double angle? Is the next question. Of course it is. Is this a double angle? It is if you want. So of course you might say it's a triple angle. Most normal people would say that's a triple angle identity, but if it suits you, it's still a double angle. This double angle doesn't mean 2 theta there. It's a doubling halving relationship. So if we have 2 theta, then this is the right hand side. If your 2 theta becomes theta, then the right hand side will be exactly the same, but it will have, of course, half of what this side has. So if the cos of 2 theta is that, the cos of theta is 1 minus sine squared of theta over 2. The same way, if you wanted this as a double angle, it's going to be 1 minus 2 sine squared of 3 over 2 theta. I doubt if you did it like that in the question, but it would have been true. So I'm going to use this line now. Let me put it around the border for my integral. So my surface is going to be 2 pi square root of 2 integral 0 to 2 pi, and I'm going to replace 1 minus bracket the cos of theta is that, and I was thinking which version I need, because I need to get rid of this 1. So it's going to be 1 minus 2 sine squared of theta over 2, close round bracket, close square bracket with a 3 over 2, and then is my d theta. Okay. So far so good. My intention was, of course, to get rid of this 1s, and I did get rid of the 1s. So 2 pi square root of 2, 0 to 2 pi, and now inside the square root, or this square bracket, 1 minus 1 cancel, and I have a 2 sine squared of theta over 2, all to the power of 3 over 2 d theta. I don't think we're done yet. It's a lot harder than I thought, this question, actually. Until you actually do it, you cannot possibly see the difficulty. It's a little bit involved. I'll tell you how many stars probably this is in my star reads system that I use in my books and my practice papers. Just do it in steps. So we're going to have 2 pi root 2. Factorizing this 2, so it's 2 to the 3 over 2. So that's another 2 root 2. That's going to come outside the integral. So I've got 2 root 2 times another 2 root 2. I'll make this an 8. I'm going to put a little note just to actually show you where this is coming from if you weren't sure what I've just done in there. 2 pi, and then the sine squared and 0 to the 3 over 2 is going to be sine cubed of theta over 2 d theta. All I've done in there, that's a 2 to the 3 over 2. That's this bit here. And that's another 2 times 2 to the half. That's that bit there, 2. And that's another 2 to the half. And adding the powers, 2 to the 1, 2 to the 3, which is just an 8. There's not the only way you can think of it. There's many different ways. I might be insulting your intelligence if we are in the last module of further maths and I'm showing you how to do surds. Okay, how do we do now sine cubed? Sine cubed, for those who know how this is done, I'm actually quite inclined in there, because my brain at the moment is not thinking very well, is to actually use a substitution. The substitution that works for this is actually u is equal to the cos of theta over 2. And if you had the cos cubed, you do the sine of theta over 2. And the same thing if you had odd powers of sine or cos, like a sine cubed, sine to the 5th. That simplifies things fairly quickly. But of course you can do by manipulation. I'm a manipulation man, but at the moment, as I said, I got the theta over 2 there, and it's my brain is not thinking very good. So let me do by manipulation just to show you what I mean by manipulation there. We got the 8 pi, 0 to 2 pi. Write this sine cubed as sine of theta over 2 times sine squared of theta over 2 d theta. Why did I do that? Because I'm going to change this into coses. So I'm going to have 8 pi integral 0 to 2 pi sine of theta over 2 bracket 1 minus cos squared of theta over 2 d theta, which is equal to 8 pi. I'm just multiplying the bracket. I'm not doing anything. So if I'm in the way, I'll move out of the way in a second. I'm just multiplying the bracket inside the integrand. Theta over 2 minus sine theta over 2 cos squared theta over 2 d theta. Okay. Sine theta over 2, that's that bit there, and then it's that times that, hopefully correctly copied. All right, that's when I move to the top. The surface of revolution is equal to. Now, why did I do that? The answer is because this particular integrand integrates by inspection. Those who are, of course, now exam standard, further mathematicians on the 4th module of pure maths, you should be able to see that. Of course, that's not a problem. So we're going to have an 8 pi. These are evaluation brackets. This comes from a differentiation of, let me actually do this one, because that actually goes plus first, and I'll leave that because it's going to go minus. It's just bad karma to do it the other way around. Okay, this one comes from a differentiation of cos cubed. Cos cubed of theta over 2. If you differentiate that, you get something which looks like that. But you're also getting, first of all, it's going to go minus, because the cos differentiates to minus sign. We've got the minus, so that's all good. We got times 3 to come to the front, and we've got times a half from the chain. So a 3 over 2 will come to the front, so we need the 2/3 to cancel it. So this is now the integral of that. And to get the sine, clearly we need to differentiate a cos of exactly the same argument. Cos differentiates to minus, but that's plus. Therefore, that's the minus to take care of it. And of course, reduce it times a half. So 2 will cancel this a half. And now we're ready to put limits and finish him off. So let's see what we're getting for that. Hopefully it'll be a decent answer. Okay, so we got 8 pi. 2 pi, we half it because the all thetas of it is just pi. Cos of pi is minus 1. Minus 1 cubed is minus 2/3. And then we're having another cos, that's a minus 1. But this minus 1 now is times a negative 2, so it's plus 2. Minus 0. Cos of 0 is 1. So we got 2/3. And this is also a 1, so it's a -2. Do they cancel out, or what's going on in there? No, they don't cancel out. Just fractions. 8 pi. Let's put equals and equals. And we got +4, 2 + 2, and -2/3 -2/3 -4/3. So the answer for that is 12. Take away 4, 8/3. I'll make it. So it's going to be 64 pi over 3. Not as straightforward as I first thought. I did say how many stars would that have been. If given like this, I think this is probably a 4.5. It's probably last question on the paper. And I would imagine to make this paper balanced, probably have some nicer questions, nicer than normal, that means, at the front. Otherwise, this on its own, just like that, I think is fairly mean. I hope you enjoyed it. I hope you follow what I've done. Who's laughing now?